Welcome to this video on force-damped mass spring systems. Consider the equation of motion for a mass spring system, including terms for an external driving force, a frictional force, and the spring force. Damping occurs when friction or air resistance causes the oscillation to lose energy over time. As a result, the amplitude gradually decreases and the system eventually settles unless an external force keeps it moving. When a periodic driving force, like F external equal to F0 cosine of omega t, acts on the system, its frequency can interfere with the system's natural frequency omega 0. If the two are close, they reinforce each other, creating resonance, where the amplitude becomes large. This raises an important question. How does the friction term minus gamma du dt influence the system's response? Exploring this effect helps us understand how energy loss through damping alters the system's overall behavior. Let us look at a specific example. Here, the external driving force F has an amplitude of 3 and a frequency omega of 1. We introduce a friction coefficient equal to 0.1. From this setup, the natural frequency of the system can be computed as 1 over 20 times the square root of 399. We assume the system begins at rest, meaning the displacement u of t and the velocity u prime of t at time t is 0 are both equal to 0. At this point, you may pause this video and attempt to compute the solution to this initial value problem. If your computations are correct, you will find that the unique solution u of t to this initial value problem is a linear combination of two terms. The first term, uc of t, is a transient term, a decaying oscillatory exponential. The second term, up of t, is a steady-state term, a sine wave with amplitude 30. This combination gives us insight into both the short-term and the long-term behavior of the mass spring. Let us decompose it into parts to understand the mechanism at hand. Now, the external driving force F itself is a simple oscillating function with constant amplitude 3. But the system's displacement u of t behaves differently. It is the sum of the transient solution uc of t, which dies out over time, and the particular solution, which persists indefinitely. The particular solution, up of t, has a constant amplitude of 30. That is, 10 times larger than the amplitude of the forcing term. As time increases, the displacement approaches the particular solution, up of t. The amplitude is capped at 30, significantly larger than the forcing amplitude. But, importantly, it does not grow without bound, as in the case of undamped resonance. This shows that, with suitable parameters, a relatively small external force can produce a very large but stable system response. This concludes our discussion of force-damped mass spring systems. To strengthen your understanding, remember to practice.